last week, we learned that if you carry out, if you try to plot a graph of substrate concentrations against specific growth rate, you end up with a curve that has this kind of shape. We said it resembles the Monod equation. And more interestingly, we said the number of information that can be derived from this curve. For example, the K's value. Can you switch off your microphone in the meantime and just activate it so that if you want to ask a question, so that the background noise will not interrupt. Great. We started this graph, which shows the substrate concentration against specific growth rate has some similarities with microbial growth curve. Please switch off your mobile phone, your microphone rather. And we also agreed that day that the section A here correspond to your deceleration phase because you have depletion of nutrient, and that section B correspond to your exponential phase because cells are greater than max. And based on those two information, we arrive at some conclusions which were on this slide here. And those information were that if a microorganism has high affinity for the substrate, the growth rate will not be affected until the substrate is reduced to a very low level, and the deceleration phase of such culture will be short. Another thing we derive was that if the growth rate, if the microbe has a low affinity, then the growth rate will be affected even when the substrate concentration is still high, and the deceleration phase will be long. Now, just to refresh your memory, the affinity is 1/Ks, that is the reciprocal of Ks, right? Affinity is 1/Ks, which is reciprocal. One question I can give to you will be to describe the pattern of the deceleration phase with respect to the affinity of the microbe to the substrate. I repeat, one possible question that it could be asked will be to describe the pattern of the deceleration phase, or describe the length of the deceleration phase as function of the cell affinity to the substrate. Then the informations, what I will expect from you will be to use those graphs as well as the information here to explain. Now let's go to something not complicated, so easy as well, but we really need to just pay attention for you to understand. Great. When we talk about cell divisions, right, when we talk about the growth of the cell, we're referring to a scenario in which going from a single cell, it will divide and give you two daughter cells. The two daughter cells will divide, give you four daughter cells, and so on and so forth. When we refer to the exponential phase, where cells divide by binary fission, this is what we have. You go from a known population of cells that will double to produce a new population that will further multiply alpha by binary fission. In other words, you go from one cell, for example, to give two daughter cells, eventually to 4 cells, 8 cells, 16 and 32. I would like you to spend 1 minute looking at what you have on the screen. Okay, spend a minute having a look at it before we proceed. Just understand that that pattern of division on the screen. Great. Now, that further implies that if you have that we have 2 to the power of 0, that will divide and give us 2 to the power of 1. Then 2 to the power of... Please, your microphone and the background noise. And ultimately, we'll have 2 to the power of n multiplied by initial cell population. Okay, please, if you don't understand, just interrupt us. Okay, if you don't understand how we are navigating, just interrupt. I repeat, based on what you have, the first line that you have here, we have from a single cell, we have 2 cells, then 4 cells, 8 cells. This is the same thing as what you have here. It's the same thing here, with the only difference that we have added the power number to it. Of course, we know that 2 to the power of 1 is the same thing as 2. 2 to the power of 2 is the same thing as 4. That means in cell divisions, you are going from 2 to the power of 0, that will multiply, give 2 to the power of 1 number of cells, and so on. And eventually, you're going to have 2 to the power of n multiplied by the initial cell concentration. Great. Let's begin to find some terms here. N that you have here is in actual fact the number of generation, right? Or the number of doublings within the time interval. I repeat, the N that you have here is a number of doubling that had occurred within the time interval T. And your N naught is your initial cell population. Now, if you take into account that N is a number of doublings, if you know the doubling time and you know the entire time of the fermentation, or better still, the time during which the exponential phase prevailed, you can easily find N by dividing the duration of fermentation. Of course, we are referring to the exponential phase, by the time it takes to produce one doubling. Entire class, please pay attention to what we have here. Let me repeat. If you know the time it takes for the cell to double, or the doubling time, you know the time the exponential phase prevailed, the duration of the exponential phase. To know N, which is the number of generations, you simply divide the duration of the exponential phase by the time it takes to double. Who is finding difficulty getting that? Who has difficulty understanding that section? Okay, let me just refresh your mind again. We go from one cell that will divide and give us 2 cells, and ultimately we're going to have 2 to the power of n multiplied by n naught, or the initial cell population. And the next thing I'm giving to you is, if you know the time it takes to double, that is to go from 2 to the power of 0 to 2 to the power of 1, the time it takes to form for the cell to double. That is going from one generation to another. That's what I refer to the doubling time. If you know the doubling time, and I know you also know the duration of the exponential phase, to find n, to find your n, we simply divide the duration of the exponential phase by the time it takes for the cell to double. Now, the first formula which I would like you to highlight in your book is what you have here, that NT equals N naught multiplied by 2 to the power of n. Let me explain each term here. NT is the number of cells at time t, and N naught is your initial cell population. The small n, the power of n that is here, represent the number of generation, or the number of doublings. Who is lost at this point? I want the same track up to this stage. Who is lost at this point? Let me repeat again. NT is the number of cells in your flask or your reactor at time t. N naught is initial cell population, and the small n, the power here, is referred to the number of doubling. Whenever you are reading this slide, always refer to the explanations that I gave to you, going from 1 cell to 2 cells and eventually to 2 to the power of n. Okay, always refer to that to have an idea why we have this formula here. Nt, the number of cells, equals n naught multiplied by 2 to the power of n. Okay, don't forget that today. Okay, while leaving the class today, even if you want to forget other things, keep in mind how to estimate the number of cells at a particular time within your reactor or within your flask. Having said that, let's go further. Yeah, before we proceed, I would like to refresh your memory on 3 basic log manipulation that you covered in high school. In high school, you learned that log of x times y equal log of x plus log of y. You also learned that log of x divided by y equal log of x minus log of y. And log of x to the power of r equals r multiplied by log of x. Okay? Spend 30 seconds refreshing your memory on these 3 high school manipulation of the log. 30 seconds, just have a look at it because we're going to make use of it in the next slide. Especially the last one. Log of x to the power of r equals r times log of x. Paola, can I proceed? Class rep, can we proceed? Michael, is it clear to everyone up to this point?
I think it's clear, sir.
Great, thank you. Now let's proceed to the next slide. Now, with this formula, how can we get n if you really want to find number of generations based on the last equation we have here? N equal n naught, sorry, multiplied by 2 to the power of n. How can we obtain our number of generations? By simply applying log on both sides of the equation, right? If you apply log in both sides of the equation, your equation nt equal n naught multiplied by 2 to the power n. If you apply log on both sides of the equations, you end up with what? Log of nt equals log of n naught plus log of 2n. That further implies that log of nt minus log of n equal n log of 2. And eventually your n is what? Log of nt minus log of n naught divided by log of 2. That gives you the number of generation. That is basically, you can obtain the number of generations in your flask or your reactor by taking log of nt. Of course, we say that nt is the number of cells at time t, minus log of n naught, the initial cell population, divided by log of 2. That will give you your n. What is n? The number of generation. Okay, that's n, the number of your generation. Let me repeat again so that you won't be confused. Nt equal n naught multiplied by 2 to the power of n. We want to find n, which is the number of generation. Okay, small n, the number of generation. And I said, if you revert to the previous slide on the basic manipulation of log, if you apply log on both sides of the equation, you end up with this formula, n equals log of nt minus log of n naught divided by log of 2. Great. Who is confused? Cornelia, are we on the same page? How to arrive at this number of generation?
Sir, may you please repeat, please?
Sorry, come again, please.
May you please repeat?
Okay. Now, the first formula, nt, the number of cells at time t, equals n naught, the initial cell populations, multiplied by 2 to the power of n. Is that one clear to you? No, it's not clear. Let me go a step backward. Okay, let me go a step backward. cells divide by binary fissions. Can you see the diagrams in the right part of your screen? There's a diagram of cell dividing to give you 2 daughter cells and so on. Okay?
Yes.
And
Yes,
if you want,
sir.
yeah, if you want to put this by a calculation, that is, we go from n, which is the number of cells initially, that will divide to give you twice that number, and to further divide to give you 4 times the initial number, will divide to give you 8 times that initial number. Now, the coefficient 2, 4, and 8 that you have here will as well be represented by 2 to the power of 1, which is 2, 2 to the power of 2, which is 4, and so on. That is, the first equation you have up here, the same thing as what you have below here. That 2 to the power of 0 initial cell populations will divide to give you 2 to the power of 1. 2 to the power of 1 is 2. And which will further divide to give you what you have here. And eventually you're going to end up with 2 to the power of n multiplied by that initial cell concentration. Now, based on what you have here, the implication is that the NT is the number of cells at the time t. That is, if you have a flask, for example, you want to find out how many cells are in the flask at a given time t. What you need to do is what? To work out, if you know the number of generations, that'll be relatively easy for you. Okay? If you know the number of generations, and what you have here is that to get the number of generations, you can simply divide the entire duration of the process by the time it takes to produce 1 generation, TD, the doubling time. If the fermentation lasts for 6 hours, and it takes you 1 hour for the cell to double, you simply divide 6, right? If it takes 1 hour, you divide 6 by 1, that gives you 6, and that corresponds to n, the number of generation. If it's taking 2 hours for the cell to divide, basically you divide the 6 hours by 2, that will give you 3. In other words, your n, number of generation, is 3. Having said that, now, what if you want to obtain n itself, the number of generations? You can apply, based on this formula, you apply log on both sides of the equations. If you apply log on both sides of the equation, you're going to have end up with n equals log of nt minus log of n naught divided by log of 2. Okay, we have used just one of those log manipulation in the previous slide. We are asked you to spend 1 minute refresh your memory on that. And again, something on this slide that is clear is that this formula is valid at the exponential phase, right? That is, we don't apply this at the lag phase or stationary phase, but it's applicable at exponential phase only. A new term, which I'm going to give to you, is a growth rate K. Now, we're going to have 2 types of growth rate here. Sorry. Here's a growth rate K. Subsequently, you're going to see the specific growth rate. These are 2 separate terms. The growth rate K, which is here, and I repeat again, these are 2 different terms. We have the growth rate K here, which is the number of generation per unit time. Subsequently, we're going to see also the specific growth rate, but for now, let's focus on this growth rate, which is the number of generation per unit time. And K equals N. N is the number of generation divided by T, the fermentation time. Of course, we're referring to the time the exponential phase prevailed. Right? We have got at least 2 terms. NT equals N naught times 2 to the power of n. That's one for the first expression. You also come with the second term, which is the growth rate, the number of generation per unit time, by dividing n by the t, which is the time the fermentation prevailed, or the fermentation prevailed at the exponential stage. Dineo, still on the same page, or you want further explanation? Dineo and Nolu.
Yes, it's clear to me.
Sorry, I don't seem to hear you nicely. Is the explanation clear up to this point?
Yes, it's clear.
Right, great. Now let's go to further term here. We already know that TD is the time it takes for the cell to complete one cycle to double, okay? If you got one cell, TD, as we have covered in the previous slide, the time it takes one cell to become two. That time is what we refer to TD. Now let me give you the first example. You're going to work it out. Let me know what you have obtained in your book. Please open your draft book. Let's do this example together in the class before we proceed. This is an example. Apply those formula, get your answer. I'm going to call you your name randomly. You tell me what you have obtained. Okay. You have here, they said a process is initiated with a single bacterium. Here's the weight of the bacterium. The exponential phase lasts for 48 hours. The TD, everybody, TD, the doubling time was 20 minutes. And the questions put to you is to find the weight of the progeny. Okay, proceed, work it out. I'm going to give you 2 minutes to work out. Then I'll call you to get you tell us what you have found. I want everybody to attempt it. Each person should attempt. Who has obtained the answer? Slindo, have you got the answer, Slindo? Have you got the weight of the progeny at this stage? Nosipo, have you got tell me what you have got. If there's anyone that has already got the answer, you can unmute yourself. Tell me what you have got as the weight of the progeny. Okay, let's solve it together. Right, let's solve it together. The first thing you need to do is what we know is that N0, the initial cell population, is 1 because they said it started with a single bacterium. We know for sure that TD, the time it takes to double the population, is 20 minutes. Right? This is information that we have. Sorry. Okay, let me repeat. N0 is the number of bacteria. The number of bacteria is 1. TD, the period needed to double the cell population, is 20 minutes. Now, if we need to find the number of cells that we're going to obtain at the end of the 48 hours. Okay, we need to find the number of cells that are going to obtain at the end of 48 hours. To achieve that, we need n, the number of doublings. Remember, we said if you know the duration of the fermentation, you know the time it takes to double, n, the number of doublings will be your fermentation time divided by the doubling times. Your doubling time is known, 20 minutes. The entire duration of fermentation is known, 48 hours. What you need to do is to divide the times the fermentation has taken, the exponential phase, by the time it takes to double, which is 20 minutes. In that case, your n, number of doublings, would be the 48 hours. Of course, you convert to minute, divide by 20 minutes. 20 minutes is your TD, the times it takes to double. You're going to obtain your n. Your n is what? The number of number of generations. Your small n is the number of generations. Now, if you go revert back to this formula, okay? If you revert back to this formula given to you here, NT equal n naught multiplied by 2 to the power of n. Do we have do we have all the ingredients at this stage? Do we have n naught, class? Sinetemba, do we have n naught after partial result? Do you have n naught? Please, I want a participatory class. I want you to don't be shy. Sinetemba, tell us, do you have n naught? Don't seem to hear her. Teresa, do you have n naught in this? Do you have n naught, n initial? Our n initial is known, which is 1, because you have only one cell starting with, okay? And do we have our n, the number of generation? Yes, we have worked it out to 144. In other words, you're going to work out the number of cells at 48 hours will be our n naught, which is 1, multiplied by 2 to the power of 144. That'll give us the number of cells after 48 hours. The next thing we need to do is what? To multiply by the weight, because you're asked to provide the weight of the progeny. We know the weight of the single cell. That is basically, since we know the number of cells after 48 hours, what is expected from you is to now multiply the number of cells at the end of 48 hours by the weight of a single cell. That will give you the expected answer. Who has obtained the right response? Okay, I could see 2. Dineo has worked out something. All right, okay, great. Let's have a look at, well, I assume that you have worked it out, that we got the right answer. Now let's go at something much more important as well, also interesting as the previous one. Should we be talking about the cell number or cell mass? Okay, let me explain something to you. If I say to Paula, I'm carrying out an experiment, or better still, I've used 5 cells to produce, I've carried an experiment with 5 cells to produce 1 milligram of insulin. If I write it in the publication that way, and Paula, I want to repeat the same experiment. She tried 5 cells. She may not obtain the same amount of insulin, right? Let's assume that my own cells were bigger cells, let's put it that way. Were the cells already that had exponential phase or bigger cells. And she repeated the experiment just with the same number of cells, but these are the cells at early stage. She may not have the same thing. The contrary, if I said I've used 1 gram or 10 grams of inoculum to generate 1 milligram of insulin, of course, it's much more easier for you to repeat. The bottom line is the following. Cells divide, they have different sizes. in industry, they'll be referring to cell mass more frequently than to use cell number, right? And your cell mass is what I use here as X. I repeat to everybody, Dineo, Terisha, Paula, and Nolu, and the entire class. In industry, cell mass will be much more frequent than the cell number, right? Because it gives room for reproducibility. Now, based on that, we're going to find out how to quantify cell based on the cell mass. The formula is the following. What you have here, XT is the biomass concentration at time T equals X naught, the initial cell concentrations, multiplied by exponential mu T. Mu here refers to what's called the specific growth rate of the cell. I repeat, cell concentration at time T equals X naught, initial cell concentration, multiplied by exponential mu, which is your specific growth rate, and T. Now, let's see how this equation can be used and what useful information can be derived from this equation. But before getting to that, let's take a clear understanding what the specific growth rate is about, right? We have already covered K in the previous slide, which was the number of generations per unit time. Now, we are coming with a new term, which is specific growth rate. In actual fact, throughout the fermentation process, I'm referring to your batch, fed batch, continuous, this term mu will be coming frequently in your vocabulary. That's why I would like you to underline what is written here. Underline it, read it, reflect on it. Okay? The bold part written in black, underline, read, reflect. Because mu will be coming frequently in your entire vocabulary in the fermentation biotechnology. Now, the specific growth rate, the way you can conceive, you can interpret is like it is a fraction of biomass per unit of time. Okay? It gives an idea how quick or how slow the cells are growing. For example, if you have mu equals 0.3, and that will imply that approximately you have 30% increase in biomass every hour. Okay? Take it as mu, it gives an idea how quick or how slow the cells are growing. Let's proceed with other with this term, the term that we have covered here, right? I'm referring to the term XT equal X initial exponential mu T. Please, I'm giving you 30 seconds again to have a look at this term. Sorry. XT equal X naught exponential mu T. Okay? Now let's see what will happen if you apply linear on both sides of the equations. Okay? We're going to transform it to a linear equation. Y equal AX plus B. I wanted to transform this to a linear equations. Y equal AX plus B, for example. This could be achieved by applying ln on both sides of the equations. You're going to end up with ln of X equal mu T plus ln of X naught. If you take a close look at this equation, hello entire class, if you take a close look at this equation, ln of X is your Y, mu is your slope, the same thing as A, T is your X, and ln of X naught is your B. That implies that this term, ln X equal mu T plus ln of X naught, is the same thing as Y equal X plus B, which is a linear equation. It's a straight line equation, right? Y equal X plus B is a straight line equation. I would like to underline the next paragraph that you have here, that if you plot ln of X against time, that will give you a straight line. If you have a straight line, of course, if you have this equation, what is the slope of this equation? Y equal X plus B. Nolu, no, I think I've called Nolu a couple of times. Let me call Nosipo. If you have this equation, Y equal AX plus B, what is the slope of the equation? This line, what is the slope? Those people were listening. Then Pinky, if you have y equal x plus b, what is the slope of this? Dokozo, who can help? Who can help the entire class on this
Is it
this
the
question?
gradient?
Pardon?
Is it the gradient? I'm not sure.
Yes. Yes, go ahead, please.
I think it's the gradient of the equation. I'm not sure though.
All right, okay. When you have these equations, y equal x plus b, your slope is your a is your slope. That's why if you align these two equations, which I said ln of x equal mu t plus ln of x naught, that implies if you plot ln of x against t, against process time, what you're going to obtain is what? If you plot ln of x against time, is like you are plotting y against x. What you're going to obtain will be the slope, which is a, will be your mu, your specific growth rate. I repeat, if you plot y equal ax plus b, if you plot this equation, you're going to have a straight line. And a is the slope of that straight line. In other words, if you plot ln of x against time, you're going to have a straight line. The slope is the specific growth rate in bracket mu. Please underline this statement. The plot of ln of x against time give a straight line. The slope is a specific growth rate in bracket mu. Write it down, everybody. The slope is specific growth rate in bracket mu. Okay, having done that, what you have here is the same thing I've just explained to you, that if you plot ln of x against time, you're going to have a straight line like the one you have here by your right. And the slope of such line is your mu. Please underline or picture this, capture it, the way you can keep it for long in your memory, because you're going to make use of this equation actually each time that you're asked to find out the mu. I'm giving you again 1 minute to have a look at it and reflect on it. At least you learned to do a couple of things today. How to obtain your slope, how to obtain your specific growth rate, how to find the cell biomass using the formula xt equal x naught exponential mu t, or using the formula or the number of cells using nt equals n initials multiplied by 2 to the power of n as well. Okay, those formula I will leave you to reflect on them, and also the tutorial question I gave to you. If you haven't got it right, go back to it again. We'll stop here for today, and tomorrow we're going to have in-person lecture on campus. Okay, tomorrow we're going to have in-person lectures during the double period allocated to you. Before I release you, is there any question from the class? Is there anyone that want to raise a question? Colin Lenospo, Slingdop, Paula, class rep, Terisha, Dineo. Is anyone that want to raise a question before we leave for today? Is there any questions? Not really. All right. Thank you very much, and see you tomorrow. Thank you.
Sir, could you please upload the Zoom after the session so we can re-go over it?
Yes, I will do that. I will do that. Sorry for the delay, but I'll upload the previous sessions.
Thank you.
Thank you.